Okay.
Okay. So hi, everyone, and welcome to the Digital Futures Young presentations. This is a really international panel today. We have speakers literally from all over the world, and we're also joined by the Young Digital Futures team.
Okay. So
and Neil Leach will also be here today. So thank you everyone for being here and joining us today. This is the first of 3 sessions with the topic computational design, and we'll be kicking off today with an excellent panel of speakers. So we also want to invite everyone to join on YouTube and Bilibili to ask questions. Just type in the question and we'll ask the question for you after the talks. So yes, please just join us and ask questions. In addition, I want to also basically tell people that we have a Discord server as a place for discussion and knowledge that is live and everyone can join. So for all that information, go to our website. And so thank you. Today we're going to start with Maria Larsson joining us from Tokyo. She's a PhD student at the User Interface Research Group at the university. And so Maria, would you mind sharing your screen and starting it off? Thank you.
Yeah, I will go ahead and share. All right. So hello, everybody. My name is Maria. And yeah, I hope this slide is loading good. Yeah, I am an architect and also a PhD student in human-computer interaction. And yeah, I want to thank DigitalFUTURES for this opportunity to present today to such a global audience. It's a really nice opportunity. And yeah, my presentation today, it's titled Digital Wood, Interactive Design and Fabrication of Wood Joints. And yeah, I'm going to present this research project. It's about the creation of a wooden joinery that takes care of the design and the fabrication and the material properties of wood in kind of one application. And yeah, this software or this project was developed by myself and with a small team from my research lab, including Yoshida Mitani Nigarashi sensei. And we have written a paper about this work that will appear in UIST User Interface Conference in October. And yeah, let me first share the background about the project. So what you see here is a collection of images of various wood joints that are used in both architecture and in furniture. And these kind of joints are very appreciated for their appearance and also like have good function. But it's actually really difficult to design these kind of joints because of the geometric complexity. And it's also really difficult to fabricate these kind of joints. And so we want to address these points by creating, we want to facilitate the creation of joinery. And yeah, within the field of computer graphics, there's already some work that has been done about joinery, including these 3 that I'm showing. But the limitation of these works that they have in common is that they do not really consider the materiality or the method of fabrication. So the results are usually presented as, or in this case, as Lego, or as a 3D printed model, or simply as graphics. So now let me change the screen to show the interface that we have developed. So it's focusing on the joint between just not like the whole structure, but just focusing on the design of one joint. And then the design space is this like 3D grid of voxels. And then you can edit the joint by pulling and pushing voxels like this. And notice how when I pull here and add some voxels, they're automatically subtracted on the other side, making sure that there's no overlap or empty voxels. So in this way, it assists the design exploration of joints. And you can also change the type of intersection by pulling it to the side. Let me do this. And the angle of intersection. This is a bit slow. So now it slides in this way, for example. And you might already have noticed there's these colorful lines and fills, and that's like real-time feedback about the joint performance. So this arrows here tells that the joint can slide down and out. But if I add something here, no, it's working fine. Or if I find another joint, this automatically updates according to the current design. So in this way, the user receives this graphical feedback about the performance while live while editing the joint. And now let me switch back to the presentation. So in summary, you set the sliding axis, angle of intersection, and so on, and then you can edit the joint. I didn't show, but there's also a gallery mode where you can choose from pre-calculated valid joints. And finally, the system exports the toolpath to a CNC fabrication machine. And these are the 8 feedback metrics that we consider in the system with the graphical feedback. And perhaps the most interesting is durability in regard to the fiber direction. I would explain this one in more detail. So we observed that wood has different properties in different directions. It's an anisotropic material. So in the direction along the fiber, it will be, depending on the species and type of wood, 10 to 20 times stronger than other directions. So therefore, parts that are sticking out like this, perpendicular to the grain orientation, they will tend to break off. So in this case, we color those types of geometries yellow, and then the user can avoid to make such geometries. And then, let's see, it's loading a movie here. So this is how the fabrication looks like with the 3-axis CNC milling machine. Milling out the joint is of course automated, and it's also very precise and customizable. And there are of course many different kinds of fabrication machines, but we focus on the 3-axis machine because that's the one that you will find in available in most wood shops that are equipped with such machinery. And this 3-axis machine has 2 main constraints. One is that it can only approach the material from one direction because it only has 3 axes. And the other one is so-called what we call the inner corner constraint. It means that you cannot cut sharp inner corners that are aligned with the milling bit if you have a normal milling bit attached. And the system also takes care of these constraints. Specifically about the inner corner constraint, I will show an example. So if you design a geometry like a plus-shaped joint like this one, if you fabricate it with a standard milling path generator, you're going to have these rounded corners here that the machine cannot cut, and then you cannot assemble the joint because this extra material will collide with the corresponding sharp outer corners. And we solve this problem simply by rounding the outer corners when they're located on inner corners. But this is not something that that the person designing the joint has to do by themselves. It's an integrated part of the path planning algorithm. And now I will show just kind of details about showing the joints that we have fabricated using this system. So this is It takes a second for the video to load, I think. But yeah, this is the design that you just saw in the 2 slides previous, this plus-shaped design. And you can see the fit is very precise thanks to the CNC milling machine. This joint has a joint in a higher voxel resolution of 5 by 5 by 5. And here is a joint that is connecting 3 pieces of timber. And in this case, it's quite difficult to find a good solution. So it's useful to do combinatorial search to find a solution. And this one shows an oblique joint. So you can, in the system, you can set any angle of intersection. And this is a furniture scale. We did 2 furniture. This is a chair, and this is a table. So what this program cannot do is angled and curved geometries. Like you can angle the intersection of the joint, but you cannot, the geometry of the joint itself, you cannot make a dovetail or any freeform curves. And you cannot make multiple sliding directions. One, because 3-axis CNC machine can only mill out from one direction. So if you have multiple directional sliding, it becomes a bit more complicated. And also it's not really made for plate-to-plate connection, it's made for like frame structures. And it could be extended to that, but it would require, probably a few additions. And finally, I wanna just, share a few words as like I'm an architect, but also now working in human-computer interaction. And my experience of when you develop a design tool for architecture, or when I have done that in the past, it's very specific for that building. And maybe if you don't normally do like a user interface, so after you finish the building, the tool is scrapped or not used again. So what I'm trying to do here is to develop the tool, and then the tool can be used by many other people to build things. And thank you very much for listening. And please follow us on Instagram, Sugite 2020. We'll be uploading some development of the project. And thank you. I'm happy to hear any questions.
Thank you, Maria. Really fascinating. So because we want to present everyone first and then ask questions, but if any one of the other speakers has questions for Maria right now, we can take them really quickly because she might have to leave us because it's so late in Tokyo. So were there any questions from other speakers? If not, we'll just move on. So the next speaker will be Laure Michelon. She's from LA, or currently based in LA, and has a background in architecture, but also architectural technologist and designer with a focus in architecture and machine learning. And she has she got her master's degree from SciArc and in civil engineering from Columbia. So Laure, take it away.
Great, thank you. Okay, so first of all, thank you for having me. Again, my name is Laure Michelon, and I have a degree in architectural technologies from SciArc and a Bachelor of Science in Civil Engineering from Columbia University. But today I'm going to present to you on fashion. Makes sense. Currently, I'm actually the assistant teacher for the Architectural Technologies Final Studio at SciArc. And my project for today is Equivocal Fashion designed through machine vision. This project is very much still in progress. The final is hopefully going to be published in late September in the inaugural issue of Export, the digital magazine and platform. I've always been interested in fashion. And while at SciArc, I had the chance to use the robot house with Karime Batliner and my project partner, Sylvia Nanu. So inspired by jewelry created by Shaw and Lane for Alexander McQueen, we designed armor breastplates using large-scale 3D printing. This was like my first foray into navigating the intersection between the digital and the physical world, especially when it came to fashion, and I just found it very exciting. So digital fashion is, and its use of artificial intelligence is nothing new to fashion design. For example, Robbie Barrett redesigned Balenciaga's line using Pix-to-Pix and dense PoseNet, which you can see here above. And The Fabricant, a digital fashion house, has also explored using CycleGAN in its deep, faster than fashion line. So in ESC, I'm exploring the implementation of machine vision and intelligence to re-examine existing haute couture collections to produce speculations on fashion. This work draws inspiration from past haute couture runway shows and is reinterpreted using StyleGAN 2, a generative adversarial network introduced by NVIDIA. The results are familiar and fantastical, ephemeral, but quite realistic. So in the beginning of this project, I was testing design outputs using both CycleGAN and StyleGAN. So CycleGAN is a technique that involves the automatic training of image-to-image translation models without any paired examples. So the models are trained in an unsupervised manner using a collection of images from the source and target domains. It's an extension of the GAN architecture that involves simultaneously training 2 generator models and 2 discriminator models. One generator takes images from the first domain as its input and outputs images for the second, and the second domain does the opposite. Discriminator models are then used to determine how plausible these generated images are and update everything accordingly. Each GAN is also updated using cycle consistency loss, which compares an input photo to the generated photo and then calculates the difference between the two. So style generative adversarial network StyleGAN is also an extension of the GAN architecture. It proposes large changes to the generator model, including the use of a mapping network to map points in latent space to an indeterminate or intermediate latent space. The use of intermediate latent space to control style at each point in the generator model, and the introduction of noise to a source variation at each point in the generator model. And StyleGAN 2 is just the second version of StyleGAN. So for the CycleGAN tests, I actually first started by drawing inspiration exclusively from single designers. So on the left from Alexander McQueen, in the center from Brick Owens, and on the right, Iris Van Herpen. The first tests done on Alexander McQueen's work was done with my studio partner, Sofia Ospina. And the results across the 3 vary dramatically, and the quote unquote mistakes are amazing. So this third leg pops up consistently. Often body parts are misaligned. And sometimes when the background and the model got confused, the negative space is thought of as the principal form. The results depend a lot on the length of training, which is to be expected, but the longer the training, the more similar the designs became, which is ultimately why I switched to StyleGAN. So with the StyleGAN tests, I moved towards drawing inspiration from many haute couture runway shows, varying in shapes, sizes, form, and color. The StyleGAN 2 created more realistic humans with distinctive and diverse designs and better ignored the background features. So haute couture has always spearheaded creative possibilities. It's an arena for research, both in terms of craftsmanship and design innovation. While the rules associated with haute couture fashion is quite stringent in the creation of the garments, they have to be custom made by hand at the atelier. The process for the initial phase of the design is very open. So for ESC, the neural networks here are sketching by generating these thousands of images. More traditional processes are done in a similar way where designers sketch and then the lead designers choose the best and those designs become elaborated on. Here are some from my favorite designers. And this kind of shows the original sketch from Ray Kawakubo and then the finished product. The forms in the sketches are easily read, and even though they're rough and lacking in detail, they clearly represent the final garment. I wanted to show these because I think she's a master of form and showing some of the most exciting couture today. But while Rei Kawakubo might sketch similar versions of these, ruminate on them, redraw them, and then choose only the favorites, I'm instead parsing through all of these images generated by AI and then collecting the most promising images. So seeing fashion interpreted through machine vision highlights the difference of perception between human and machine. Machine vision can see things that we can't. It can interpret images in ways that we can't without creating or relying on our own biases. Machine vision identifies interesting patterns and perspectives because it doesn't possess human perception. It's unrestricted by aesthetic capacities and inclinations. The results are elaborate and not always predictable. 3D technology allows for the freedom to push boundaries, giving designers the ability to visually explore new digital shapes, textures, materials, and colors. This new form of digital fashion returns to the heart of what I think fashion was always meant to be, a playful and creative space to express our design identities. And without the constraints of human taste and style and history, the neural network comes up with designs that might never occur to a designer. So because StyleGAN 2 models using only 2D visual imagery, it doesn't have to take into consideration fit or tailoring. So while these distorted and nouveau sketches are exciting, moving to the next stage of design and bringing this into 3 dimensions required the next phase in the design process, where sketches are curated and then translated into sewing patterns. This process requires a speculation on what these generative forms are. And acting as the lead designer, I speculated on the sketches and created these sewing patterns. The patterns shown here are stylized in their representation for sure, but they are real drafts to be used to sew these garments. And I'm going to go through some of these set of sketches and their associated sewing pattern, kind of showing how the garment is broken down. So for the first dress, it's a body blouse top with set-in bishop sleeves and a below-the-knee balloon skirt with a V-shaped bustle overlay. The second is a double-breasted suit jacket with tight set-in fitted sleeves, a micro mini skirt, a large sporran, and slashy thigh-high boots. This is an A-line shift dress and a clear asymmetrical poncho with a large cowl neck. Then a floor-length ball gown with a bustier top and hidden inseam pockets. This shows an A-line micro mini dress with an empire line yoke top, a cold shoulder, set-in lantern sleeves, and a sporran. Next is a wrap top deep V maxi dress with a large semi-stole cape. And finally, this dress has a short bolero jacket, a micro mini peg top skirt with a large Manhattan peplum and round hip wings. So as I said earlier, this project is still in progress. Moving forward, my next steps are twofold. I'm currently working on physically constructing and sewing some of these patterns into their physical manifestation. You can see one of my Clo 3D models on the right here. I'm also working on a pix-to-pix model of a design paired with its sewing pattern, so as to possibly be able to generate patterns from these design speculations from StyleGAN. I view using AI and machine learning as a tool, but it's a tool that's driven by algorithms of brute force approximation, which is a term co-opted from Matteo Pasquinelli's The Nooscope, a visual manifesto of the limits of AI. The AI is used to design many unbiased, new, and different options that can be edited, refined, and tailored to fit the designer's ideas. And the aim of using machine learning in this design process is to develop an alternative definition of couture. So, thank you.
Thank you. So same here, if there's any clarification questions, please ask. But I have a question because I know that Maria might have to leave us early. So I wanted to address it right now because we got one question for her on the YouTube chat. The question is, let me read it out to you. 1 second. Where did we go? So the question was, hi Maria, thank you for the presentation. I did not understand how you design an optimized connection between the wooden frame. I mean, how would you design? How would you decide the design you choose is the best one? And this is from Parnas.
Oh yeah, so it's sort of a design interface. So there's not one best one, but of course it has some restrictions and some things that kind of you should avoid doing, but it doesn't tell you among all the joints that don't have any problems, they're all okay. There's no one right answer. It's as the person that makes the joint likes it to be.
Okay, thank you.
Software. Yeah.
And thank you, Laura. That was really fascinating. So I think we're gonna move on, if no one has a question for Laura, with the next presentation. That's gonna be Tyler. Tyler from Kirk, currently working at Turf Design, an acoustic product design company. And maybe you wanna say something more about your background, but you're calling us from Chicago, and
Yep.
we're fascinated to hear what you have to say.
Let me share my screen here. Okay, yeah, I'm Tyler Van Kirk. I'm a computational designer at Turf Design. Yeah, we are an acoustic product manufacturer. This study is not on acoustics, but actually on image and form. I'm looking specifically at how 2D image and what the inherent qualities of a 2D image can lead to a new understanding of the form, and also how a form or a surface can then be reinterpreted as a 2D image. So this sort of workflow kind of consists of 4 points, starting at an image, converting that image to a series of points, to line, to a new solid, and then the inverse of changing that solid into an image. So looking at this image, it's just a picture of the Forza resonating lamps in Team Lab Borderless in Tokyo. So this is just a sample image to look through this study. If we can reduce the resolution, we'll be able to sort of see this translation at an easier scale. So we pick like a pixel here at random, like 22 pixels down, 4 pixels over. In this case, that's pixel 801 in the series of that image. And we get the RGB values of 110, 44, 112. So when we're looking at those RGB values, how can we actually populate them in 3D space? So the max values for all color is 255, 255, 255 for red RGB. And so all sort of points or studies that have to deal with color in three-dimensional space have to take place within this 255 by 255 by 255 box. And so when we're looking at the box, the actual vertices, sort of these point colors, starting at 0, 0, which is black, your z-axis is blue, your y-axis is green, and your red axis is red. So your RGB is directly X, Y, Z. But then you get secondary vertices of your cyan, magenta, white, yellow, and green. And so this is sort of the environment that these sort of studies have to take place. And I've been calling it like the color gizmo. And so like all sort of studies, you can see like where these are sort of pulling towards different colors or how they actually take up this space. So back to this pixel 801, 110, 44, 112 in 3D space, we're looking at somewhere between red and blue. It's about in the middle of the box. So it makes sense why it appears purple. So when we do that for the entire image, the 1,862 pixels, we get a cloud like this. If we increase the resolution, we get, a larger form of the cloud to represent the entire image. And we're just sort of looking at this in 3D space. You can see where it's pulling towards the cyan and magenta very strongly, and almost pulling all the way to the edges of the box, showing that there's more saturation at those corners. The closer you are to the center, the less saturation. So here's just some other studies. Here it's toucan in like the jungle, you're seeing, greens and browns, but that very strong like orange and yellow sort of line trailing up. Looking at more of a monochromatic palette, like with these coffee beans, you're seeing a straight line between black and white and shades of gray, and then underneath that, shades of brown, sort of creating a plane in itself. Here with a more colorful picture in Tokyo, you can see there's a lot of primary colors from the billboards, and that's sort of causing the form inside to sort of stretch to the points and sort of take up more space in the color gizmo. So the question comes, when we map these points out into the space, what happens if we move them or change them in some way and then reinterpret them as a new image? So looking at this most bluntly, we can see like if I pull these corners, at the top towards magenta, straight down towards red, you can see in the second image that what was those bright magenta lanterns are now red. And this has nothing to do with the proximity of the pixels. It just has to do with those. So like, the colors that are being affected aren't right next to each other. The pixels right next to each other aren't being affected, but the colors themselves that those pixels are representing. And then like looking at how grayscale is handled, all shades of gray exist on a line between black and white. So it would be 000 to 255, 255, 255. So if we project all these points from the cloud that we're given onto that line, then we're outputting a grayscale image. It's much easier to do this in Photoshop, I'll admit, but it's interesting to see how these sort of three-dimensional forms, three-dimensional transitions can represent 2D image and common image manipulations. Again, here, if we're looking at doing something like a simple attractor point, in this case, we're pulling all the points towards the red corner, which is giving us a more red image. The interesting thing too is that although the point cloud is smaller, it has the same amount of pixel data, same amount of information, just the distribution of color is smaller. So the form represents differently than, or the space point cloud can represent differently than its image. Again, here, if we move the point cloud in random directions at random vectors, what would the responding image be? And you can see the point cloud, the resulting point cloud is very unclear. It doesn't look anything like its original cloud. Yet when you're seeing the image, there's some grain to it, like you would add grain in Photoshop, but the image is still recognizable. So it's not necessarily always a one-to-one representation of like how we manipulate these in points and how the image comes out. It can vary. And so when we're looking at how these points are mapped, in order to sort of connect these points as a line is the first step in like spatializing it. And so again, if we use this image and pick sort of 2 pixels at random, looking at like 6 pixels down, 18 pixels over. So we have these 2 pixels that are right next to each other, but are very different colors. So we got like a red and a black. So when these are, put into the color gizmo space, you could see that like the line is pretty much as long as you can get actually from 2 pixels from black to red. So even though these pixels are right next to each other in 3D space, they're represented very differently. So when we look at these sort of line networks of each of these pixels in sequence are then connected and then recolorized in the space, we can see a network representing the connections of these pixels and their color values. So again, with some different sort of versions and different iterations. And so moving on, changing that line and populating that as a solid is the next step in sort of getting this final output. And so here using the low resolution image is in order to have less lines. So like the solid generation can happen more smoothly. With a higher resolution image, populating it as a solid would be a lot of data information and would probably, crash my computer. So looking at it as a small resolution image, but using a Grasshopper plugin called Cocoon, which aligns like small cubes assigned to these curves at different charges, and then it wraps like these cubes in a new mesh. So it like sort of formulates this solid mass of these networks as a solid form. And so by using the vertices of this new mesh in this color gizmo space and applying that to colorize the mesh, you would get something like this. However, you sometimes get results like this, and this is actually the first result I got. And as intriguing as I thought it was, I was curious as to why it was happening. What I determined is, like, if you could see, like, towards that magenta corner, that the solid is outside a bit of the color gizmo space. And so any point that's outside that 255, if it's like 256 even, that color doesn't exist. So what's happening is it's skipping that color in the list of colors. So each color that's being assigned to the vertices in the mesh, there's not the same amount of colors as there is vertices. So it's then shifting, this sort of color information throughout this mesh in interesting ways. And so we could sort of recreate this, like see it at different degrees as we're reducing the amount of points available to colorize the mesh. So the less points we reduce, like in here, we're seeing more of a normal color distribution. As we reduce here, then we're going to see more patchwork, and this information has to be like shifted and pulled and across the mesh in different ways. So here is kind of like a final visualization of like one of these image studies. So it's really, a solid connection or visualization of these connections of pixels, but it's also wrapped in this skin that is reminiscent of the image, but at the same time, it is its own sort of image, its own sort of object. It is both reminiscent of the image, but it is its own thing entirely. Again, sort of looking at these closer, how we can see sort of the contrast and how this sort of mesh skin sort of envelops and where it creates pockets of light and dark. So here we can see just this study again, looking at the toucan in the jungle. But some sort of interesting things is, first off, with the skin and patterning, it's reminiscent of like the jungle itself. So it sort of is speaking to its image indirectly. And then also the way that the color distribution works, it almost acts as it supports its own structure. Like there's no need for there to be structural support in this case, yet just the way that the color responds in the image, it is like a self-supporting sort of construct. Then here looking at the more colorful Tokyo image, we can see, a lot of the bright primaries didn't like take dominance over the form in terms of the skin. But we could see some really bright like yellow vertices and some of those primary colors sort of massing into a gray. So there's never necessarily a clear exact output from this sort of method. So here looking at this solid final representation, just looking at how does it sit in space, what sort of parameters does it produce, and then again, how does it relate back to its image? And even as like its own solid, is it truly independent of the image, and how does that still relate back to its image? And so then looking at the inverse of taking a new surface or a new solid and how that is then going to be interpreted as a new image in itself. So looking again, starting very simply, just having a surface within this color gizmo space about midpoint between. We break that into lines, series of contours, and we can divide those lines into points. And all those points can then be read as a single image. So in this case, with just a plane, it really just represents that color in that one area. So it's really just a gradient from all four corners. But we're not limited to the size of the surface when we're producing this image. The dimensions of the image are derived from how the surface is processed. So if we contour more lines, we'll have a taller image. If we divide those lines into more points, we'll have a wider image. So if we start to manipulate these surfaces, we can sort of see like how these manipulations represent themselves in color or as in images. So here we just have these bulges sort of showing and the sort of how it's representing as the image. And so then if we sort of exaggerate this and create more drastic changes in surfaces, you can see that the image itself, again, is like reminiscent of the form, but it's not just an elevation. It's not just a simple color elevation of the form. It speaks of the same language, but again, it's still of its own nature. So the image and the solid can speak different languages. So if we sort of look at these studies again, like we're not, locked into the size and dimensions of the surface. It's just how we process the surface and the resulting images. So we can get surfaces different dimensions that can be very different just by stretching or pulling. And then looking practically, looking at how everyday objects or how products we design can be interpreted using, this sort of method. So looking here at the light bulb, we're starting at like this brownish gold at the bottom of the light bulb. And then as we're going up, we're seeing more vibrant color. So if, it was a perfect cylinder, we'd see that brownish gold or like tones of brown all the way up. But because, it's a light bulb, when it, expands like that, we're seeing much more, vibrant colors, along this area. So the form, the image itself is, representative of the form. And so thinking how we can use images like this to, document form, or like when we're designing form, or to identify form. Again, here looking at like a plant pot, you can see how, starting, you can clearly actually faintly see the line of where the lip of this sort of area is expanded. And you can see it's still the same color value, but the saturation is much higher when it's, sort of expanding out towards the ends of the box. And so, using these sort of methods, how can we understand form if we were, designing an object? If we're seeing like drastic changes in color, maybe the surface is too rough, or maybe, something needs to be changed, manipulating the surface. So just to leave with this, so overall, this is just sort of the diagram of these sort of processes, again, starting from an image, translating all those pixels into points, networking the connections of those pixels as a network of lines, generating a solid from that, and then reskinning that from the visual representation of the image, but not a direct image itself. It's a standalone object. And then the secondary workflow, which is taking a surface, contouring into a series of lines, which then to a series of points that then creates an image, again, representative of its solid, but also of its own nature. Thank you.
Yes, thank you, Tyler. Really fascinating. Any clarification questions from the group? I think it's really fascinating, but maybe we can get to some questions. I definitely have some questions for you.
Cool.
We'll get to questions after, including the audience. So now we're moving on to a group project, a team from the AA, the DRL. They were developing their project under the guidance of Patrick Schumacher. And I would like to ask them to introduce themselves, because not the whole group is here, so I don't want to make any mistakes. So Madhuri, do you want to start?
Okay. Yeah, I think everyone is here except Vicky for now. So hello everyone. We are Xiangfan, Chen, Kidu, Miroslav, and Madhuri here, and we are team Vortexture, and with the topic future of work. We're from Patrick Schumacher's studio from ADRL, and today we'll be presenting our outlook to finding radical means to redefine future of workspace. The office building is a typology that typically finds its root from historical and social context, but is shaped by logics of economy, technology, and culture. Each era demands for itself a different setting, including Taylorism, Brunel and Shaft, action office, cubicles, and most recently seen networking office. But when we think of future work in a city like London, where technology is taken over and hierarchical order is fading, we rethink new patterns of workplaces that brings a new certification of work. In office today, we meet, we tweet, we chat in lounges, clubs, incubators. Work is everywhere. We're co-working, having group meetings, virtual meetings. The new creative workspace call for an insatiable need for flexibility, for agility, where kinetic components, phenomenological gestalt switches, and semiological aspects give rise to an architectural space. So we put forward an architecture space called Vortexture, and our project is time sensitive. Vortexture is season sensitive. On weekdays, the office orients itself to create a productivity-based space, while during the weekend, the floor plan reshuffles itself to create a creativity-based plan. Likewise, in winter, people stay inside the envelope, and architecture allows more sunlight into the building, while for summer, the architecture is more exposed to sun, where more terraces and landscape are open for the neighborhood and outside activities. The exciting part of this architecture now would be that it would generate different environments rather than one. It would therefore offer multiple possibilities to the user in the same space, creating our future work. So as you can see here, the canopies are open for people to come from outside and work, while in winters, the canopies are closed, and this turns into skylight that let the lights inside the building. So to put forward our thesis, Vortexture is an architecture space that is agile, activity-based, and there is no permanent physical form, but it's a space in constant fluctuation. Furniture and light are in relation with each other too. The formal spaces have lighter and bright intake of light for work zone, while in contrast, there are warmer colors for leisure spaces. Furniture design is correlated from being subject from same parameters of field condition. Different turbulence or vortex should originate different pattern form. We use photochromatic material to create furniture property that changes color in contact with light. Therefore, the formal space is exposed to light and changes furniture to white, and informal spaces are dimmed, changing colors to darker shades. One of our unique furniture is this wing panel or interactive screen. So when the weightless wing is lifted up, it can be used for interactive screen exposed to larger meetings. So here you can see we use curving patterns for us for the wing as well as for the canopies. So different kind of geometries were used in different aspects of the project to test out this kinetic movement.
According to Kelvin Helpott's fluid dynamics study, the flow will change from linear to curved to vortex depends on the context factors. The furniture organized align the field lines generated by fluid dynamics. Individual workings always align the linear one, while illustrates also more stable feature, and the curl and the vortex one will mainly for the meeting and discussion condition. The capacity of small working space is 1 to 14, and the frequency of movement of the furniture is higher. They will share leisure and creative space. Multifunctional working space provides more functions than individual working space to meeting and even workshop and creative and leisure space at the same time. And also the different scales of change are considered so that they can change from small group to large groups, or for small meeting to large meeting.
As a change in demands often happen, the field redistributes. When the space is formal, it's less turbulent and more concentrated with bright, lighter and furniture. When the function is semi-formal, it takes its mixed aspect. And when informal, the field is less turbulent, more turbulent, showing more viscosity, creating more dynamic environment. So here, when you can see, like when the field is apart from each other, it's creating more opportunities for formal spaces, while when the field is closer, it's more dynamic. Go next. Based on that, we developed a physical model based on the Arduino system. So we wanted to actually test out our animations into real life, and we developed this the physical model with like several actuators and servos faked, and two Arduinos talking to each other and creating these movements to actually happen. So for example, here, this is a physical model where the model is already coded, and it's all calculated in an optimized way where the furniture travels 2.2 meters with a 45-degree angle rotation, and the panel lifts up based on the curving pattern, which we already discussed before.
The organization of the furniture follows the field lines, which are reflected in the ceiling pattern, and then the furniture will control by the division points information from the ceiling, so that during the entire process, the ceiling shape changes first, and arrangement of the furniture change according to the ceiling close, so that the continuity of the fluid dynamics is reflected. The linear ones showing individual workspace, and the curved ones are the meetings and discussion, and they will change from flat to spatial form to become the partition for these activities.
In order to fabricate our ceiling, we programmed a robotic arm and print some POA on top on the TENS fabric. And as a result, we have a distinct three-dimensional pattern, which differs only in the way we tense this fabric. So you can see here.
And this is the unit we designed for the rotational slabs to reconfigure the working space to small one to large one. This is the scenario showing the condition when the isolated slabs combine with stable configuration around it and generate a small size working space, and then they are combined to another small rotational slab to become another condition. And the ramp between them linked to the leisure space on a different level to be creative and transportation. Changing the parameters of the simulation, two types of fluid dynamics results are chosen. By phenomenology, the flows are in the ambiguous conditions which can be triggered by the kinetic slabs, and their relationship of the figure ground will switch because of the dominance of the space has been changed by the movement of the rotational slabs. The whole building consists of 3 levels with rotational slabs and fixed working space. The actual working layout can be changed according to the activities. There are 4 types of conditions from working to leisure, which has corresponding configuration of the furniture organization, light, and floor organization. This is a physical model for interior study and optimization. Interiors. This is interior scenario to show the semiology for the navigation.
And here you can see like how the whole building works as a function, and from the light changes, the furniture also changes. So it's a building that is working as an engine by itself based on the activity of time, weekday, weekend, or seasons. Yeah.
We use fluid dynamics in order as an approach to design our design components. As you can see here, we use it to design our shell prototype, and we associated the fluid parameters with the volumetric parameters of the shell. Then going to our site, we use the same approach, but in a macro scale. So we again simulate the fluid dynamics, associating the fluid with the flow of people as we take in consideration their starting position and their direction, and then we design our building based on this simulation. And our building is composed also from a shell and a transformable element. In this way, we can control the environment and the scenarios that we want to produce and we want to control. In our shell design, there are different aspects. So here you can see like an outdoor cinema that we can use in the summer case scenario for outdoor activities. As we are part of a big campus, this is Stoke Newington campus, we design our proposal in order to activate the in-between spaces, to activate these streets as a public shared spaces. Also, you can see the nearby school, how we integrate the school area with our inside landscape. And we can use our transformable elements to control the environment and to provide different use of the same space. Here, for example, is a normal working den, and on the next slide, the transformable canopy. If you go to the next slide, the transformable canopy is up, and this is like a public event with some social interactions. If we look here, we can understand how the user is perceiving the information from the building. For instance, we can see the open roof, which means that there is an event happening on top of the terraces there. We use material properties plus curvature from one hand to integrate our design with the existing surroundings, and from the other hand to develop and define these kind of public in-between spaces, and to activate these important spaces between our design and the existing building. In order to activate all of these properties of our building, we design a Signify system, which is composed from structure, stairs, and a roof. It is in the core of our building design. And if we go to the next slide, we can see how we test this via building a physical model. Together with AKT, we are developing a hybrid structure, which is composed from arches, a space frame, and all of these transformable elements that we discussed. In order to test our idea, we built an agent model where we can simulate human crowds, and we can test our design proposal and its properties. Hope this fact is going good. Yeah.
Thank you, everyone. That was a lot of work that you guys did. Thank you for sharing that.
Yeah, thank you. We had one more slide, but it's okay.
Okay.
Yeah.
You want to share it, or
are you ready to share the last video? Because I think it's very important. Yeah. Yeah, here you can see how we tested our design via these agent models. Yeah, I think maybe we can go.
okay, thank you.
Yeah, thank you.
So if there is no question from the group, first of all, thank you everyone so far for presenting, and I know that Maria might have to drop off, but yeah, 2 more presentations and then we'll enter into a discussion, so everyone can prepare their questions. And now we are moving on to Alberto Fernandez Gonzalez from the Bartlett School of Architecture. He's doing his PhD at the moment there, and he will be presenting, I think he's based in London right now, right? Okay.
Yes. So, well, share the presentation. Share. Here we go. Everything's working well? Yeah, I think. Well, firstly, my research is cellular architecture from discrete grids to a high-resolution space. This research started years ago in the master course led by Alejandro Sec and Jose Sanchez as TA, and now is follow the MPhil and PhD path with Mario Carpo and Roberto Botassi as tutors. So, well, what is a cellular architecture? It's seeks to integrate the application of cellular automata simulations to architecture as growing design process in contrast to the top-down design methods that commonly we are applying in the architectural field. So what is a CA? Well, a CA is a set of cells with binary states in basic configuration 0 and 1 mainly on a discrete grid that can evolve throughout a sequence of steps and time, who was firstly developed by John von Neumann, an Hungarian mathematician, who tried to develop a self-aggregated system for different purposes. So now this research tried to expand the automata theory to the architectural field, recognizing the theoretical background of computer science as an opportunity to develop conceptual and physics models based on generative computing with origin on a seed cell or called automaton. This cell follows the steps over a discrete field, which is this universe. So in this research, we will see the application of the Langton and CA, which was created by Chris Langton in 1986 as generative seed that mediates with the problematic of crystal growing simulation, recognizing rules and at some point that function as mediator between cells, state, and space. So it's one cell which is transforming their own environment, and then is trying to build a different shape according to different set of rules. So the most simple configuration is a cell in the middle, and then is developing a loop, and then with from the beginning to the end, and then a second loop in other direction, and then it's moving to other place. So multiple seeds can generate different shapes by their interaction in the same discrete field. So 2 and 4 and 6 are creating a complex scenario and a high resolution scenario just based on zeros and 1 on black and white. So then the translation of Langton and from 2D or to a 3D discrete field allows us the possibility to explore different possibilities in this three-dimensional environment. So here I have 3 examples of that. And with that, we can enrich the number of possibility solutions inside the same discrete universe. So at this point, I worked with a discrete field with us in between 25 centimeters by 25 centimeters mainly, and then just changing the direction, it's possible to develop this integrated scenario. So here we have these 3 examples that, and with over that was possible to recreate a negative and a positive development as a lattice structure. This lattice structure shows the result of possibilities as a 3D lattice system. And it's really fun because at the end, just few changes can create these completely different results. So this is an opportunity for design. Then the second stage was trying to achieve the interaction between this CA with a simulated environment. So for that reason, the code addressed an image as a 3D restriction system. With that this restriction system, the Langton and CA recognize such a kind of neighborhood in a negative way. So this is really important because at the end, this seed is looking forward or looking around their own environment. So it's taking their own decisions according to these restrictions. Then the next step was trying to understand the possibilities with this code, addressing and adding different bitmaps. And then the result was a variety of shapes that can come from microscopical patterns to urban shapes, changing at the end the result of this simulated universe. And then I add an agent behavior to the 3D Langton ants based in code. For what? Trying to achieve a better coordination between these different cells. Trying to understand as well that there is a nice possibility to coordinate one seed to the other one, and then the combination of this collaborative work could produce a much interesting and integrated result. So how to translate this discrete set of points and its relation to a spatial solution? So from points and lines in a discrete universe, as we can see here, So in this simulation, it's easy to understand this coordinated seeds working all together and reading bitmaps as a restriction and as a possibility to develop different and complex scenarios. So to a solution between discrete and continuous architecture. So this is really important. We have a discrete environment, but under this discrete environment, it's possible to reload or reconfigure a different result as a different shape using, in this case, a spline. So at the end, we are generating an architectural approach that translates discrete to continuity. And of course, using different patterns. So as an example of that, this is a collection of points following a generative sequence based on evolutive movements. So a generative shape from the first point generated as a set of discrete elements is an option, a classic one. But then there is a second option, which is a generative historical path from the first point generated as a linear scan. And then a generative historical path from the first point generated as a continuous spline. So at the end, it's such a kind of historic translation from this collection of points, from the very first one in the collection to the last one. And at the end, it's a complex threading system. So the same set of points from the last discrete solution could be translated as a continuous spline and in a spatial solution. So from this digital model with this test to a 3D printed solution as a second stage with a linear scan, an hybrid scan, as well a complete recursive scan. So from discrete grids to a high resolution space. So what is this? This first simulation, or full simulation. Here is possible to understand as well the behavior of this Langton building these highways in this three-dimensional space, building columns as well, and other different possible manifestations of architecture. So what is this? It's such a kind of hybrid. It's discrete, but at the same time, it's continuous, working together. More and then could be possible as well to develop something more integrated and something more or less dense according to the patterns from images from the real context or from microscopical examples as well. So a next step was trying to create a more complex proposal. So for that reason, I add this radiation solar system from a real context. And with that, this 3D Langton ant by CA revealed a unique geometry, highly coherent from the beginning to the end, with points, layers, and rules working all together in this code. So this is the example of this discrete scenario. And then later, this was the final result at that stage. So again, it emerged the same behavior, but in a different way. Highways and columns, and then more and less density according to radiation. In this case, with more radiation, more code working over. Less the radiation, more open space. And then the final result is this idea of integrate space. And at this point, the discrete grid was developed in a sequence of 20 by 20 by 20 centimeters. So it's quite dense. From a structural point of view, this was reviewed by IKT2 engineers trying to understand the spans of each structure. So that was addressed as well in the code as part of a real input for this development. So the final result consists on a highly dense collection of discrete points that can be treated with different geometries, using points as arrangements of new elements on this intricate space. but this is the beginning. So we have a collection of points, and this collection of points can create this, this scenario. But then probably it's possible to reload the same collection of 3 discrete points with other criteria. Just an example. In this case, this is a continuous surface instead the spline strategy, but it's using the same collection of points. So this is at the end probably the most important thing in this cellular architectural approach. It's an architecture based on activation of or deactivation of this discrete grid and the relation between them, and then it could be possible to replace this collection of points with any different geometry. It doesn't matter if it's a discrete one or it's a continuous one, or the interaction of both. So at the end, we are adding possibilities and in this variation of cellular architecture in the future. So the next steps of this research is mainly focused on trying to test different versions of CAs with different cellular architectural manifestations. So replacing, I insist, points with different shapes, with different elements, and then testing it in physical and in digital way. So, well, this is it. Thank you very much.
Thank you, Alberto. That was really great. Thank you. So if there's any clarification questions, if not, we're moving on to our last presenter today, Hossam. He's currently at the DARS studio, Design Architectural Robotics and Systems studio at Dessau Institute in Germany. So welcome, Hossam.
Hi everyone. Hi everyone. My name is Sam. Today I'll present my thesis proposal, Generative Sandscape. The main part of my research was studying the deserts around the world. As we know, like 33% of the land of the Earth is considered as a desert. The main problem about the desert, it's when any human interaction or development happens in the desert starts crawling on it. Like we see here, the abandoned city of Madam in UAE, it's completely covered with sand dunes now. And I was inspired with the say from Borges: "Nothing is built on stone, all is built on sand, but we must build as if the sand were stone." So this made me think like I don't have to think about sand as a barrier or as a challenge, but we can use it also as a great additive or advantage. Then, as was my studio, the mainstream is robotics architecture. So I was studying how to build a structure with robot, a sand structure with robots. And I studied mainly these two examples, like this to the right, sand spray. We mix sand with bacteria and start solidifying. And a second one was fusing the sand with solar energy to create a sand structure. I also studying some proposal in the desert. The first one to the left was using the sand dunes as a mold, and the second one using the physics of the sand to generate the forms. Then I zoom to my my country, Egypt, because 93% of Egypt is considered as a desert. And now the Egyptian government is building, planning and 15 new cities inside the desert. The main challenge about building in the deserts, like here is the example of the new capital, Cairo. It was designed by SOM. The main design was supposed to work with the natural patterns that happen in the nature, were built through hundreds of years. This satellite photo was taken around 2016, and after 3 years from the construction and the main spine of the city started appearing, we can see most of this natural patterns are totally vanished. Yeah, and what expected to be happen is what already happened in the first part, New Cairo. Now in the rain season, all the city are covered with water. So yeah, we have to learn from nature. There's no designer, there is no better designer than nature. So I start zooming into my location, which is Siwa Oasis. It's in the middle of the Western Desert, and it's 600 kilometers from Cairo and 300 kilometers from Al Alamein, the nearest big city. It's literally in the biggest sand sea in the world. Starts from Egypt going to Morocco. Then this is photo of the oasis itself. It consists of two big lakes, and the city are in the middle. Yeah. And the reason I choose Siwa because it's a long history of dealing with desert like buildings and building with sand. They have their traditional material called karshif. They make sand with salt to create this structure. This is the old city center. And this is a contemporary example of architecture made with also the tradition karshif. Adrar Amlal Hotel, Eco Hotel. It's without any electricity. People go there just to meditate, and it's one of the most expensive hotels in Egypt. Yeah, when I was analyzing the urban growth of the Siwa Oasis, the city, I discovered like most of the urban growth happened in south, not in the north. Through 30 years, I studied that, so I was wondering why. But when I zoomed into I found like north of the Siwa Oasis, there is this sandstone hills, and in the south, it's just sand dunes. And the main direction of the wind is northwest. So we can see here like this sandstone hills were carved through hundreds of years with this direction of wind. And this point, I get to study this cycle of life of sandy grains, from being sandy grains to sand dunes to solidify to be a natural process of solidification to be sand rocks, then sand hills, then the erosion happens and it's sandy grain again. It's the sand life cycle. And I also studied each stage has a human activities that could happen during this stage. And this was my iterative design process. It's like a closed feedback loop. That means like any change happen to the macro or meso or micro scale affects the whole design output and the end. But it's all inside the loop. Yeah, when I was studying the sand shifting and the erosion, I have to find something in common so I could design with it, and it was speed and force and time of the wind. So that made me to classify my human activities to static and dynamic physical spaces that can people use during specific time or season. Yeah, and I was really inspired by this photo again from Javi, It's like one photo has a lot of information. The one bird is flying, you can see, and the track, it's all flying during all the frames here, just in one photo. Yeah, what it's if it goes more complex, but here you lose the trace. Where is the start point? Where is the end point? So I was thinking if we give a color for color gradient from example blue to purple, and then we can know where is the start point and the end point. I start here using the same logic to simulate 1000 particle in a flat surface with a certain amount of force and see how they react. And so we can see the particles, and here is the sand travel diagram, how I call it. Yeah, and this video we can see like in the left is a particle, and in the right is a sand travel diagram. In the sand travel diagram, you can record all the information in one photo, in the final photo, but to the left we lose all the previous frames. Yeah. Then I neglected the gravity of the from the simulation and did it again, and this was the result. Then I choose the specific place from the oasis to design as a new urban extension growth in north of the city, not on the south. This site contains sand hills, sandstone hills, and also sand dunes. Then I run the simulation again. This is the particles, and this is with the sand travel diagram. Then I have to see how the sand travel diagram changes, or how the sand movement changes with when we change the topography or the topography deformation. So I did two tests, one with extruded topography and the other with curved topography. The first one, this curved, then the extruded. Then I analyzed the results. I found like mainly the sand or the sand pattern or sand travel diagram goes in the same ways, exact ways, but what changes is the density and the speed and decay of each situation. So if we want to analyze this two situation in both example, in the extruded part, the decay, the speed and decay are less because the sand travel in two different directions, but in the curve it's more density and has a higher speed. Then I took just one strip of the big site. It's 2 kilometers by 400 meters. Then I did my iterative design process again. I had to know where the sand dunes will happen. So I did this simulation. This was the first simulation to know where exactly I will have the sand dunes and how big, how high is it, and the amount of sand I will get. Then again, I did the simulation sand travel diagram. Then this made me decide like I have two different zones. The first zone is the sandstone hills, and the second one is the sand dunes, where it consists. The first part will be affected mainly by erosion, and the second part will be solidification. And this is the first zone when the erosion being affected by the sand travel diagram. Yeah, and this is the final result. Yeah, and in the second part, it's the one will be from the sand dunes. And again, here I was inspired by this picture, like how the sand dunes react when it meets an obstacle. So my building actually will be made as an obstacle. So the sand start piling, and then I use this sand to print my building. So yeah, and I took this. I used this experiment, the wool thread experiment from FryAuto, the same concept, to create my shell with the counter. Yeah, I created my shell with a counter force of gravity and speed. The speed of wind and direction. And here I was optimizing the building program with also the dynamic and static spaces. The red one are the static spaces and the other one are dynamic, trying to get the minimum area and the minimum intersection between the spaces. Then here a zoom in. I get the outline, then this is my building program, the final one. Then this is a circulation. I connect the circulation to the different floors, spaces, then my structure fixed point. Then this wires are get more density according to the opening size. I need to make it as smaller as I could. Then the simulation starts. Then this is a building structure, the skin, and this is the final. And here we can see the exploded of the building. We have we do have like two different type of skin. It's one high transparent layer acting as the doors and the openings, and the other one is building skin. It's low transparent. The floor plans. Yeah, some section we see it's a continuous process, like always a ongoing construction site. Robotics are working here. Yeah, this is the interior of the building. Have also this idea, of course. Yeah, and this is the final master plan if everything's done. Physical model. It was also done by the robot. Yeah, and this is where just imaginary robotic who will build the building, and the building structure and the skin and high transparent layer and low transparent layer. And this is ongoing construction site where the sand come and then the robots start to print. Basically what I said, like it's like we have to inspire our design from nature because it's the most significant designer. So yeah, it's like a loop. If the some inputs change, the final products have to change and be adjusted to it. Yeah, and I'll leave you with this video that describe the whole process. Thank you.
Thank you. Thank you very much. That was fascinating. So thank you everyone for your presentations. I think now we're gonna go to questions from the audience. We have quite a few questions on the YouTube live chat. And since Maria is still here, I would like to start with asking questions to her so that we can, you know, we're not getting in strange territory with going too late here. I have one question. Maybe we can go around the Digital Futures young team to ask questions from the audience, but also questions that we have or other speakers have. So I want to kick it off with asking one question that comes from the audience. I'm probably going to say this wrong because I'm not good with Korean names, but Kyu-sung asked, did you have strength tests according to assembly systems for your wood system that you presented?
No, we have not done structural testing.
Okay. And maybe I can ask the next question also for Maria. Why do we need to use machinery then traditional woodshop tools is more productive, cost less, and doesn't require expensive machinery training and is more ecological? Sorry, that's from Elena.
Yeah, I think I wouldn't, yeah, it would be, I will try to keep it short, but I wouldn't agree that it's a competition with the traditional workshop tools. I think they can do a lot more things that we cannot do, but it's really difficult to learn how to cut joints and it takes a lot of time. So I think it's only a small subset of people that has the capacity to do that. And it is costly of their times, maybe not the tools. So I would believe that like a CNC system is more cost efficient. And as for the ecological emission of using a CNC machine, I think it's worth to think about like what's human labor versus machine labor, but I don't think it's that much. And I think using like I do care a lot about sustainable like design and architecture, and I think that there are other sustainable values just in using the material wood, and also if you can use this kind of intrinsic joints without glues and nails, it's easier to recycle, easier to reconfigure. So I think in the bigger picture, it can be like you can use it in an ecological way. But I don't want to. I think the traditional craft is great, and I don't think that the system is in competition. Like it's either like make joints by CNC or by hand. I don't think there is like either or kind of thing. I think they will continue, and now more people can also make their joints if they want. Sorry, that was a bit long answer. But
No. And I just saw that you also posted the link to your project on the YouTube. So anyone that is interested can go to that link and check out your website for more information.
Maybe I take one more from Mario. I know that University of Tokyo is doing great in terms of woodwork, and I really invite all the audience to follow their works. And the work that you presented here was a very focused work, which was discussing an application. And I was really fascinated also to see your teammates. Also Hiro, who I know from Delft, he was studying his PhD, and his idea was to basically use the scan data of the wood and inform the tooling and the design process. So I wonder whether you are considering some sort of similar strategies, because you were discussing how, for instance, the design space and the production space can inform each other. And I wonder if you have some ideas about the way the material space, so to say, can inform this wood joint design process in specific.
Yeah, no, I think that's a really interesting question, and that's something I'm thinking about, and just drawing the inspiration from the traditional Japanese joinery. The master craftsmen, they chose a particular type of wood, or they even plant the trees in a particular way to use it in a particular part of the building. And they prefer the north side to the south facing side of the tree, because the north facing side grows slower and has therefore denser material properties. So there's definitely, there's definitely an opportunity to analyze like the microscopic but the small scale like features, or even bigger scale features of the wood, and use that for design of joinery in particular. And I think that's it's very difficult to do computationally, and therefore interesting to research. And we had that's about the joinery, and before this project we were working also together with Hiro, that you mentioned, in a different project about like using the shape of branches and use that for design, so that you scan some weirdly shaped wood or not straight wood that is completely natural, and then try to match that to particular shapes. So that's definitely, I think, an interesting like theme together with wood, because it has such diversity. Thanks for your question.
Thank you.
Yeah, and also it changed the way how you produce. Hello, Maria. I'm Marina. I'm from Argentina. So yeah, I didn't introduce myself. No, also this idea of production, it changed the time that you use, and in a way it changed a little bit not in a great. I mean, from in a bigger perspective, if you think about Japanese philosophy, how it takes a lot of time to do this design, and it was part of the philosophy. I mean, it's related with the time of the tree, or something related with it. So I was wondering how, what do you think about this change in time? Because now it's like super fast. You put it in the machine and you produce it, and even the time to think about the join is faster. So what do you think about to change this part of the conception of the joinery, of the join in the wood?
Yeah, you definitely, I mean, the person crafting the joint, they have a much more closer connection to material, of course. And it's always like, I mean, anybody that has experience of seeing a shape in the computer, whether that's a whole building or for an architecture you designed, or if it's something you're 3D printing, there's always some moment of surprise when you have the physical room or the physical art, the 3D printed artifact in your hand. You're like, oh, I thought it was going to be a bit smaller, or this material texture is a little bit different than I had imagined. So, yeah, I think that's related to the time, like that when you craft a joint, you spend time like directly with the material. Yeah, so that's lost. But what you can do instead is you can do many iterations. So I personally learned about joinery by failing. Like, I thought this was going to be a good joint, and I produced it, and I was like, oh shit, this doesn't work because of that. And then, yeah, with this increased speed, you can do many iterations. And I think that's a different way of learning and exploring and spending time.
Yeah. No. Anyway, I seen the website that you have like a picture with the mistakes, with a big picture with all the. And I think this is interesting because it's a way to learn, to make a mistake and to try it again and to try and again, I think indeed that process is not lost. maybe is the time would change, is a kind of a dislocation, or we are running faster than before. But I don't know if it's something bad or good. I'm not judging it. Just to pay. It's just a reflection about your work. Just it is great. Thanks.
Thank you.
Could I ask a question to Hossam? Is that? Are we Victoria?
Yeah.
Okay.
Sure.
Yeah. So just thank everybody. It was really great to see such a range of work. I mean, really interesting. Truly global. So I just want to Hossam. First of all, it's great to see Hossam there too. I started teaching at DIA in 2003. We had 10 people there, literally, and now it's a kind of massive school. And it's great to see that Manuel Kretzer and Sina are supervising this kind of work there. And I also wanted to say that actually the whole thing about Digital Futures world was based on the logic of Dessau, that actually talent is everywhere in the world, but not everyone can afford to go and study at the AA and so on. And so to set these things up for free, open up and democratizing the world of architecture is, that's the whole project behind Digital Futures world. But I've got a question for Hossam, and I think that the work is actually kind of very interesting, but I think there's a really challenging issue here, and that is the fact that you can't use desert sand for concrete, for example. I mean, the Burj Khalifa was built, although it was in a country of sand, UAE, it was built using sand from Australia. And that was completely environmentally unsustainable to have to go and ship sand from Australia to get there. But secondly, we're running out of sand that we can use from construction because we can't use desert sand. So that becomes, I think, the kind of crucial issue. So I mean, and I'm not sure, I know that, for example, that there are some 3D printing technologies that are used by, I think Michael Hansmeier uses, I forget what it's called now, voxel jet or something like that. There's using sand, a 3D printing technology. But I suspect that also with that 3D printing with sand, you can't use desert sand. Now I know there's some kind of like, there's some research going on where you can convert desert sand and use it. I mean, the problem is it doesn't have the same kind of profile, the same kind of texture that allows it to bind properly. And there's some research going on where you use urine to go and to make this kind of this chemical reaction to make it happen. But I think that's the real challenge, is really the fact that we can't actually use desert sand for concrete. And I doubt we can use it for 3D printing either. Obviously, maybe you can for sintering.
Yeah. I didn't go in deep in the material research, but as a beginning of my research, of course, I studied a lot in the material. I found two examples. Basically, one is I don't remember the names exactly, but there is a company now producing sand blocks with microbial parts, it's completely natural process without any additive chemicals. It's all bacteria that bind the sand together. And there's also another research is being formed. I will post the links because I don't have it right now. But of course, if we have to build a very large scale structure, we have to have also additive like steel for now, for example, inside the structure. Yeah.
I mean, I think there are ways of getting over that sort of that question. I work with Berojos Neves. We're working on a 3D printer using regolith for the Moon and Mars, and there are ways of kind of maybe using fiber, inserting fiber into it, and so on. But it remains extremely challenging. Just to go back, the company. There was a professor who had been, or a former professor at the American University.
Philippe Bloch. No, yes, also Professor Philippe Morel. I'm sorry, Philippe Morel. From France.
But I think the problem is that it's a very slow procedure, right? It's very, very slow to do this. And also the quantities, because they were using urine for this thing anyway, the quantities were just so vast. So it remains the big challenge. And if we could find some way of doing that, where you really do large scale construction using these technologies, then it would make a huge difference.
Of course, yeah.
We managed the workshop at the American University in Cairo with Professor Philippe Morel and one of his PhD students called Ahmed Hussein Izzat. He was developing the technique of additive manufacturing using the sand and some kind of salt. He is mixing this sand and salt. It makes some kind of crystals from this sand, and then it solidifies within a certain period of time. I was involved in that exercise as a workshop. Also in testing, he was generating kind of different blocks with different material mixtures and so on, percentage of sand versus the salt used. It was very interesting. Also, we have other researchers called Dr. Dina in the British University in Cairo. She developed a kind of block from sand, tested to be used for the same buildings, sustainable structures, but it's a 3D printed block, just a block as a discrete element, which will be aggregated somehow to generate the full building. So there is Philippe Morel for 3D sand printing. They developed a very big achievement into the research, and the other one was Dr. Dina. She developed these discrete element that will be aggregated somehow, generating the full structure. Maybe Hossam can check these two projects. They may help.
Yeah.
So I've got another question. If there's no one else asking a question. Sorry, to go to, is it Laure? Laure, the SIARC?
It's Laure.
Yeah, Laure. Yeah, I guess, I mean, with cycle GANs and style GANs, the real problem you've got is going from 2D to 3D, right? This is the real challenge. I mean, plus control, that's become the kind of key issue. And I guess that if you kind of, architecturally, we can sort of get around that to some extent because we use 2D representations. So I'm thinking here of Stanislav Chailu, ArchiGAN and so on, where he just kind of operates in a 2D world, but you've got a real challenge with fashion because you're working from 2D to 3D to 2D in a way. Because I mean, in a way, you've got to be able to sort of to map out the 2D fabric from a 3D model. So you've got to go from the 2D GANs to 3D to 2D. And I know there's particular software there, but that seems to me the real challenge. And I can't see how you're going to get around that without becoming completely manual. In other words, there must be a lot of your work which is actually is not AI based, but kind of top down human intervention.
Yeah, I mean, especially for this project in specific. I mean, so again, this project started with looking at haute couture, and the rules associated with haute couture mean that it has to be like handmade by humans. That's specifically written in the rules of if you want to consider yourself an atelier. So in terms of that, I think this works well because you need a lot of human intervention to go from sketch to pattern to 3D. And I was that human intervention. But I think that there are ways to incorporate more of machine learning within that process. Again, like in thinking of pix to pix and how that translation between sketch and pattern can be learned. I know, for example, for architecture, like that's already being explored by multiple people. You know, looking at a building facade or plan, from either elevation or for plan, and then generating architectural plans based off of that. So I'm actually okay with using this as, again, this kind of like brute force approximation. I think in the grander scheme of computational design, much of what was shown today is like based off of like mathematical algorithms that are precise. And I don't think that AI is that at all. And so I think that it's okay to speculate on what these like irregular forms are and then, you know, use human intervention to create that.
Yeah, there is certainly the University of Michigan, Matthias Del Campos collaborated with Alexa Carlson, who was on a couple of weeks ago, where they used PyTorch 3D. But I mean, that's incredibly energy-consuming project. But,
Yes.
Yeah. Okay.
Yeah, maybe if I can jump in here. Actually, I had a question that was very, very similar to the one that you were asking, and so maybe I can pick up from here. Also to Laure, specifically to this relationship between 2D and 3D in the GANs, no? So in fact, on the contrary, I was very fascinated by the fact that you were working with 2D patterns in fashion, because somehow I think in that way you overcame the constraint of working in 2D of the GAN, but let's say in a way the GAN was not working on the three-dimensional outcome, the final result of the dress, but you were working, you were forcing the AI to work within the logics of the tailoring, no? Within the logics of the craftsmanship of the tailoring, no? And so somehow the interesting thing is that basically I assume the GAN would work within the discipline of tailoring, without any knowledge of a human body, no? Because all the learning will be just on patterns that are abstract, for the machine. And in this way, so the machine will have intrinsic knowledge about the human body that is embedded in the patterns of fashion that have been evolved throughout the centuries, but would have not any knowledge of the human body, because there's no three-dimensional information that is input in the GAN. And so perhaps I actually wanted to ask you if you could elaborate more about how, this, then the process of going back from the pattern to the 3D was happening.
I mean, I think that is so interesting, just as an idea, and goes back to my kind of obsession with machine vision, in that it can see so many things that we can't understand yet. Maybe one day we will be able to, but and so in taking the patterns and putting them back into 3D, I really tried to stay true to what I think they were. And in Clo 3D, you can just, you draw out the patterns of what they are, and then you can help see how it will fit within the human body and try and manipulate that to match what came out of style again. But the interesting part is that AI can generate some very different things without, very far from what we think of as fashion design, but a lot of times it also just looks very realistic. In fact, like a lot of the ones that came out of this that I didn't end up choosing look like suits. Pretty straightforward, and which I love because I would definitely wear them, but maybe they were less interesting.
Maybe a follow-up with what Antonio mentioned with regards to abstraction, and also following up with what Laure presented. It seems that like when we work with these AI-based systems, we tend to start from the solution space, right? So we tend to start from the solutions that are acceptable and available. So you start with the, 1,000, 10,000 solutions. You look into the different fashion designers, and that solution space provide basically based on that solution space, you develop a design system and then work with that. So, and in this context, I think the role of abstraction is really important. Like, for instance, if we see the work presented by Tyler, where he was starting from a very abstract mode of representing color in space, and then this became a kind of a generative tool to translate something 2D to 3D. So maybe my question is that where do you see the abstraction happening when we use this AI-based system, and how we can avoid not necessarily get lost, but like being taken by the solutions that are available in the input sets?
I think that's an interesting question. When you're talking about the input sets, do you mean just the actual data set created before in order to train the models?
Yeah.
I think that building data sets is like the most important part of training any neural network, because that is really where the control of the designer comes in, because what you put into it obviously informs what comes out of it. And the more you play with this, the more you realize how you can sort of guide or navigate these neural networks. Obviously, you cannot control them. Like, these are not specific design tools in that sense. But I think in cultivating that data set and therefore, you know, imposing your own bias, that's kind of the first level of how you get these abstracted forms in ways that you want. But you bring up a good point and I think that that's something moving forward that everyone who works with AI is dealing with. So right now, a lot of it is just, you know, you see what comes out of it and you pick your favorites. And I don't think that that's enough, but I think that it's where you start. And that the next level of abstraction, whether it's through, yeah, I mean, the idea of using color to inform what comes out in 3D, I think, is an interesting topic and something that some of my students are working on right now, actually. So that's kind of fun. But yeah, I guess I don't really have an answer for you. More just that it's definitely something to think about and that it's interesting.
Yeah, interesting topics.
Yeah.
I think I just want to make one short point, kind of connecting to what came to my head when I was watching you, Laure, and Tyler's work, but also the others. I think it's interesting because we often have that kind of projection of our own interest in this project onto the project itself, and kind of that becomes a driver for where you're going. But then I sometimes, for myself personally, think it's really interesting because you said the machine can see so much more than we can, but also humans can see so much more than we expect. So I think it's kind of interesting to challenge yourself, seeing things differently sometimes. And when I was watching Tyler's presentation, I for some time got really interested in what's called chimerical colors. So those are colors that we actually don't expect that we can see because they fall outside of the space that is normally mapped as the perceptual space of color. So after images, for example, we deal with this on a daily basis because of screens. We see it every day. And I think it's interesting to kind of, when you approach a project, kind of going in with this kind of knowing that maybe there's more than what you expect, and kind of seeing these different outcomes when taking yourself out of it and going back. So I think it's interesting just as a way of working, and that kind of came up when you guys were talking about the machine can see more, maybe even the human can see more. So kind of this process. And yeah, I just want to challenge everyone to kind of think that way. Anyways, I think yes, sorry.
No, sorry, please finish.
No, I just wanted to move on to the questions from the audience, but please.
Okay. If I can say one last idea about machine vision, and especially the bias. I think at some point there was mention about, you know, that sort of unbiased productions by the model. They're not really unbiased. They're biased by the data set, of course. But an interesting place to look for what the machine maybe sees, we definitely don't see, and maybe to look, understanding how these are generated is probably like by doing something on model interpretability. And this is something that Chris Ola, I think he's in OpenAI now, has written a lot about. His blog is really amazing. It's one of the best places to read about that. And what he does is he tries to understand what are the elements of the image that the neurons, especially essentially the model, react to, and why and how much and how do this correlate. So he builds this maps of feature importances and all that. And in there you can I think learn something new about what the model sees and creates, more so than the results themselves, because the results themselves in this type of models, they're always an interpolation of the input. They're not really anything new, like in the sense radically new. But I think the way the model kind of identifies this image, that might be interesting to see. And I think that there might be already infrastructure, like software, that can do that for this type of guns. And maybe that's an interesting step you can look into.
Yeah,
Thanks.
I have the same point as Theodore. I will just would like to ask you, if when you do the cycle GANs, when you do the network and then have the image, the final image of the design, and would like to produce that design, you should convert it or extract some kind of 2D drawing to cut the fabrics and so on. Are you doing it manually, or you have some kind of converting this RGB data into a surface using some kind of like grasshopper and then generate these curves, or you just generate it manually? I think if there is some kind of automated conversion production for these lines from the RGB surface, then the lines would be more helpful to minimize the human interpretation, maybe.
Yeah, at the moment, this is all by hand. It's done by me. As I said, I am working on training a pix-to-pix model. It's taking forever to go from these kind of sketches into their correlating patterns that are, I mean, the difficult part with this is that since pix-to-pix kind of reinforces whatever designs that you're teaching it, the patterns need to be ones that you kind of agree with isn't the right word, but that you want to be producing with. So I am working on that. I kind of was okay with this project being more manual in the sense that it is falling under the world of haute couture. But yes, I think that using color as a way to analyze these images would be an interesting step.
I think what's interesting though about even the way that it is now with you interpreting it, you know, like, and you're using the language of fashion. And like, as we're thinking of machine learning and AI and stuff, it's like, how do we treat it not as a tool, but also as another designer? In a way, it's like a machine's giving you a sketch and you're saying, what do I make sense of these sketches? And so it's okay that it's not a complete, you know, 3D representation, you know, of, you know, what it's proposing, because it is like a sketch and you're then interpreting it as the designer. So I think there's different levels of how we can read output from machine learning and how those sort of workflows can be different, like working with a teammate as opposed to, you know, a tool with a specified output.
Okay, thank you.
I have a comment in relation with something that Victoria mentioned. And it's related, I'm super interested with the blind part of the processes, the part that we don't see. And this, that's the way it's related with this screen perception that we have and how we work with images all the time. And I was interested to know if Laure think that in a way you can reinform the process with the experience of the matter of the fabric or things, how you can, or how do you imagine that you can reinform the process in this part that you don't see, but they are absolutely important in the contact with the body, for example, or in the way that you, sometimes the perception of the image is not total. I mean, you can see just, it's a partial view and you have a lot of blind points in your design all the time. And my question is that how do you think, how do you expect to reinform your process with the material experience, with the way how you build it this way?
It's a good question. So far, I think without really thinking of it in terms of that, specifically with like materials, for me, it was just going back and editing the data set, or starting from different checkpoints depending on what I thought was more useful or more interesting. So in that way, that's kind of a more traditional way to use both CycleGAN and SalGAN. But I think that going back to reinform it based on material properties would be interesting, and maybe that just means splitting up the different models depending on what sort of output you want and being more specific in terms of that, but I'm not sure.
I mean, just kind of make a comment. I think to say that the machine see things we don't see is maybe not the right way to put it. I would say that that depends on the data set you're using and what you're training the AI on, right? So it'll be trained to see things as indeed we are trained to see things in a certain sort of way. An example I always give is a rainbow. You know, kids are told there are 7 colors in a rainbow, but there's not. There's a whole entire spectrum. So I don't think it's they're seeing things we don't see. It's actually a different way of thinking about things.
Yeah, I do think that is an oversimplified sentence that I used, but I think, yeah, totally fair.
Sorry to cut this off, but I just wanted to go back to the audience questions so that we don't let them wait too long. So there was a question for Vortexture. So what method did you use for the fluid simulation into the 3D form of the building? So I don't know, maybe you can answer that quickly for the question for the audience.
Hello. Well, we built this fluid dynamics in Houdini, and we simulate them in this environment, and we use the parameters for the fluid as viscosity, turbulence, and fluidity, and we associate these parameters with the volumetric parameters for the shell. Then we design the shell in Maya, and the process was back and forth, Maya, Houdini, Houdini, Maya. This was about the simulation and bunch of other softwares. For example, we programmed the robotic arm in Grasshopper, and also we built these agent models in game engine in Unity, and use like C# and Node algorithms to set the behavior to the furniture and to the human agents.
And then there was a second question for you guys. The first question was from Evan, and the second question is from Aya. And she said, a great presentation. I'm curious how disabled people are going to walk on these kinds, in this kind of office. Is there any consideration of inclusive principles on the design?
Well, of course, our idea is that this kind of working environment is open to everybody. So everybody can operate and find its place there. So, of course, I agree that it needs more optimization about the inclination of these of the ways to the terraces and all. But the idea is that everything is kind of automated, and with the transformation of the building, you can reach the space what you want as easy as possible. So it was taken into consideration in the very early design stages.
Maybe I have a question for Alberto. It is fascinating to see that how like the use of cellular automata, which we can somehow also categorize it under agent-based modeling, and in a larger, maybe under a larger umbrella, they are part of what we know as complex adaptive systems, the way John Holland is putting it. So one question that I have when it comes to computational design in general, since you are an expert in cellular automata, so how do you see the way, because they are very much rule-based, and there is a certain level of randomness, but at the same time there is a certain level of let's say control. So how do you see the application of complex adaptive systems and cellular automata in general when it comes to controlling and basically making the cellular automata or agent-based model more context aware in a way?
Oh, it's a really good question, because according to the research till now, normally we have, as you told, rules, and these rules are in some way controlled at the beginning, but then the interaction between seats is in some way unpredictable. Yeah, but few things that is possible to address in this CA is that when you put images from the context, as I try to develop in this development, is the way in which I can control more, or I can predict in some way the final result. You know, so with more restrictions, then this CA is more in some way predictable in the result. So you have more control if you add more restriction as context. So if for that reason, when the research started with a completely freedom, you know, it's this empty box and nothing more than rules, all the results are in some way a little bit random. Yeah, so, you know, you have some emergent behavior as a highways just in case, but adding other restrictions is in some way is the way in which it's possible to have more such a kind of predictability in the full system. And on the other hand, if you increase the resolution of this in this lattice system, as well, it's really possible to, in some way, to add more elements, more seeds, and at the same time, the CA is in some way disappearing, and then a shape is emerging more than just the CA. So that is the other way. And the third level is trying to work in different layers of coding. So probably you have a certain kind of CA working on their levels, you know, as such a kind of mass behavior for foundations, you know, and then a second layer of CA starts when the first one ends, and then the second one could produce more columns or, you know, some kind of stairs, and then when this job finished, you can add a third level, which is just a kind of roof on the other. Everything is about training at the same time, your CAs. You can create a huge amount of different variations, but then you must select specific ones which are really useful for specific purposes in your architectural development. So it's a matter of time. So it's really long at the end, the job here, because it's, you know, in a three-dimensional way, you must test a lot. And then you can save the very best examples. And then with those examples, you can try to work in different combinations, trying to achieve such a kind of a certain level of design instead of just randomness.
Thank you.
Mm-hmm.
If I can ask a question for Madhuri, Xiangfan, and Miroslav. First of all, thank you very much for your presentation. I really love the subject of plasticity. I think that's how I understand it, like how we can embed plasticity in design. And maybe I have a question and a half. We will see. But the initial thing I thought of watching the proposal is that, do you think, and I want to ask you, do you think that plasticity has to always be complex in that sort of way? And I mean, like, if you want to embed it, do we need movement, reshaping, and, you know, like explosiveness and all these things, or can it be equal impactful, you know, other ways, like simpler ways to embed it, like maybe perhaps, you know, like small actions that could change, for example, the usage of a space? Is that something that you experimented with or explored, or was the only way to completely reshape in form and function? Yeah, I hope that makes sense.
Thanks for the questions. We use the shape not only like something aesthetic, but we use it like in order to navigate the users, to navigate people into our design. So following the curvature or seeing different kind of materials, seeing different kind of lights, all of this complexity is needed in order to differentiate spaces and functions, or in order how one space can perform with different functions. Let's say if we change the light on this space, the function change. If the curvature is different, let's say if the curvature is different, so the performance in this space is different as well. So this is how we associate the complexity of our design.
Okay, thank you. I'm only making this point because I think it's a very crucial aspect of the future design or the design of the future, this plasticity, especially with climate change. And if we see like differences, climate impacts coming, and there are a lot of buildings around us that are not plastic at all. So I was thinking like maybe it's an interesting research to think of like how we can transform these buildings if it's possible. So think of ways to change function and form without completely radically changing the form. That's why. So I think you've started on a very good direction, and I wonder if in the future maybe it's something you also
Anyway,
it can 3D printed using the 3D sand printing Hossam was experimenting. It might be helpful in constructing these organic buildings in a way of using a sustainable material. Yeah, if they, I think they are already using some kind of research, a lot of research using sustainable materials in the outer skin. I think that may be very helpful in the future. Yeah.
Anyway,
thanks for the question.
Anyway, one thing we're struggling with this in architecture, no? With this idea of change and things moving and flexibility. Since I mean, it's something, it's an interest that we had before, but we didn't get. I mean, we are not doing something. That it has this real movement, at least. I mean, because in a way you presented how you can move the furniture, for example, to have new organization of the space, and you can move also elements, architectural elements. I don't know, you want to move the parts of the building, and in a way it reminds me to this building in DigitalFUTURES in New York with up directly the big part of the buildings moving, and we have like this idea that we want our buildings alive with natural, in a kind of a natural but not natural exchange. But the reality is, when I see the designs, the result of the designs, you see an static building. You don't see, I mean, of course that is not static because it's exchanged matter and I don't know, energy, a lot of things, but the shape is static in a way. I mean, it's building, it's there. And then I was wondering about the exterior change of the building, for example, because when you see the change of the city or how you can, I mean, I saw this picture, you use a Marais picture in one part of the presentation. And at the same time, Hossam shows this picture of the fly of the bird, which is related with Marais studies as well. And finally, the idea of movement in a building is not related with the shape, and it's not related with the construction. It's related how the building interacts with human and non-humans, and it's more related, I think, in a way. I don't want to go to theoretical discussion, but I think it's more related with assemblages. Assemblages not in the way that assemblage just part of like with as we see in goods, but assemblages with the society, with the change of the city, with the climate change. So in a way, this idea of flexibility of movement is more related with it than with the idea of the shape have to, or all the building have to move. One part of the building have to move. I think it's just a comment, because I'm seeing all the time this. We really want that our buildings have been. They could be like organisms living in the city and have all this change idea. But I don't know. I don't know if we are there. I don't think so.
Yeah, well, our proposal was to speculate these ideas and to what extent we can think that we can do this kind of transformation in a large scale, and also to use, talking about the shape, to use the shape not only, as you said, as an aesthetic, but in order how we communicate with our users. What does it mean? Why the shape is like this? What is the meaning behind it? So yeah.
Yes, but finally, what is important is what we see about buildings, how we understand buildings. If we understand buildings as processes, as a building really is, is something that is changing all the time because of different aspects, users, as you said before, for example. The problem is the view that we have of architecture. The problem is not that all the buildings have to, I don't know, like a walking city, for example, or something like that. It's not necessarily this, but I think that the problem is our conception about the buildings, and it's not so related with the shape or curves or things like that.
Yeah, I agree on that.
I have some questions for Taylor. I don't know if we should move or we have time. Victoria.
Yeah, you should ask your question. All right, please.
Okay, okay. It's 3 questions actually. But your work was very amazing. I love it. The way you have done the mapping, creating the solids and so on. My question is how you deconstructed the RGB colors to X, Y, Z, and then at the final, what software do you use? And then to the final, you generated this solid. What software do you use? I'm a bit confused because I'm using Rhino and Grasshopper and so on, and I think you used other platform. I don't know what platform you used. This is my first question. The second one is you said that you considered the color translation from a bird is will generate a kind of a structure that is somehow stable. How do you think we should investigate and check the validity and the stability of these structures, not just depending on it's a real structure that I manipulated using its image, so the generated is also stable. And the last one is do the designer any charge in manipulating these points while generating the solid, or the engine that converts and deconstructed the RGB is the one who is in charge? Yeah. Thank you.
Okay, so first question, software that I use. So I developed about 3 or 4 different scripts. The ones like to translate an image from the image to a series of points. So that's its own script in Python using the system drawing interface through Iron Python. And so, I'm able to reference the colors and then have them output directly as points into Rhino. Those points are also named in sequence. So if I do move those points, I run a secondary script that reads those names. And so it knows how to reorder those pixels and still, output the image. If the points weren't numbered, then, like all those pixels could go anywhere and there's no recognizable image, even though all that data sort of is the same, it still needs that series of order. So those are sort of the 2 scripts of like taking an image, or taking an image to a series of points, and then using those points to turn back to an image. Then there's the other script that is taking a surface or a solid, and that's like just using like it's another Python script that's contouring that surface, and then dividing those contours, into a series of points, and then it's then reading those XYZ values, and then retranslating, doing the opposite of what the first script is doing, and translating that into RGB values. So that's the sort of the software. And then like with the sort of generation of the solid, the sort of sculpture forms at the end is using Grasshopper and using like the Cocoon plugin that allows it to sort of formulate as a mass. So that's question 1. Actually, and I'm not remembering question 2.
Question 2 is the one you say that you use the bird as a real structure, and you said that when you translated it into some kind of meshes, it will be stable because the bird is already stable and the image. So the idea, I think we need to check. Somehow you need to check the stability. So
yeah, I mean, that was just like a natural sort of finding. These things, they don't need to perform to gravity at all. It's just pixel information. But there's ways that maybe we could create, that we can analyze it, and then I can go in Photoshop and just use like a brush, and then interpret that image. Like if I know what a stable structure is in 3D space, there's a way I can translate that to an image. Then I could maybe manipulate that image and then reinterpret it into 3D space. So I mean, kind of using these tool sets as a way, to look at design and to just formulate, something in 2D to 3D, and like sort of and it's not maybe not necessarily be as useful, but it just as an example of like how we can look at these sort of processes. Like, I mean, it's not as, it's not like a structural simulation or anything, but there's ways that form and color and image are sort of representing themselves without us necessarily realizing it.
But I think Amoeba, so a plugin into Grasshopper may help. I think it's working with this kind of geometries. You can check. The last question is, does a designer any charge in manipulating these solids generated from this amazing process, or the script itself is the one who is in charge? There's a Python mind you created.
Yeah. So the process, I tried to look at this, and there's a lot of things, that we have similar language for different sort of natural phenomena. So like we describe color and sound, in waves, and, like RGB can easily translate to XYZ. So there's a lot of just these sort of inherent data that is in certain form or certain methods that, can be translated. So I tried to like, not have as much of a hand in the authorship of, this work. It's strictly like the pixels. I guess made a decision in terms of how the lines would connect the pixels, but it is in sequence of the image. And then, really the choice, I guess, came from me in a bit with, the skinning of the system. I can choose, how many colors are used, or, reducing that amount to get more drastic effects in sort of that skin system. But I think the idea, really with this study is to see like what's inherent already there, and like, how can I, say represent something that is an image and say, like this is that representation. Now it both speaks to the image and how it's also its own thing entirely. And actually, if you ran it through the script again, it'd be its own image. So I mean, these could be cyclical, and you just sort of have to see like where you pull out the best results.
Okay, thank you.
I think there was one last question from the YouTube, and that was to Miroslav. Can you control the lines printed on the cloth to control the shape, or you just use computer software to simulate? Is it the same result?
Well, so the result of the cloth is based on different parameters. So one is the pattern that we set in Grasshopper. And the other one is, let's say, the material that we printed on top of the cloth. Like we use PLA, but if we use some other material, the result is going to be different. And also one of the main parameters is the tension that we set to the cloth. So if we set bigger tension to the cloth, the result is going to be more deformed. And if it's less tense, so the result is not going to be so much deformed. So there are different parameters that control the deformations there.
Great, thank you. Well, thank you everyone for the contributions and the interesting discussion. I think it's really interesting how different the projects are, but in the end, how much they actually share in terms of ideas and approaches. And in the end, we all come together under the umbrella of design and architecture. So it's interesting how different the approaches are. Yeah, thank you. I hope everyone enjoyed the discussion. And please follow us on the Discord board and maybe engage in the conversations there. We try to keep that open to everyone to participate, and maybe you have ideas or questions that come up after this. So yes, go to the website and maybe join the Discord board. We'll be happy to meet you there.
Could I just add something to that? Thank you so much, Victoria. This is fantastic for presenting this. But I think if everyone could kind of just spread the word about this, we're having this every single Saturday, and especially the AADRL guys, letting your colleagues know about this, because I think this is a fantastic forum to show your work. And we're going through every single week from now until next summer when we have the big workshops again. So please try and spread the word so that everyone can partake in this. But I want to really thank not Victoria, but also not just Victoria, but also the presentation today. It was really great to see this very super inventive work. Thank you so much, and thank you also for the team for their feedback and questions. Thank you.
Thank you.
Thanks, everyone.
Thank
And thank you, Neil, for
Yeah.
putting all this together.
No, it was you. It was you. It was you. Thank you. Thank you to the team.
Amazing presentation.
Thank you, everyone.
Thank you.
Very good job.
Bye-bye.
Bye-bye.
Bye. Thank you.
Good night.
Bye.